All right, so in this video, I just wanted to briefly cover this idea of expected value in statistics. So given a random variable x, right? Random variable just meaning it's not deterministic. Sometimes one thing may happen, sometimes another thing may happen. And there's these certain outcomes, each of which has its own probability, right? And you may have seen this equation or formula in your statistics class, right? And it might look intimidating or confusing, but we can pretty easily break this down, right? So as we said, random variable x, capital X, we would read this then as expected value of x, right? So the expected value of x is, we know capital sigma is a summation. So the sum of these lowercase x's are each outcome. And this p of x is the probability of that outcome, right? So if we were to translate this to regular English, right, we would read this as the expected value of x, or we could say the expected value of the random variable x, if we wanted to be super specific, is the sum of, right, that summation, that sigma, each outcome times the probability of that outcome. Right, so hopefully that makes that a bit more clear, right? And with these expected value problems, typically you'll get maybe a table or it will describe a series of outcomes. Let's call that x and the probability of that outcome, right? So maybe we have 0, 1, 2, 3. Maybe these happen with probabilities 0.2, 0.3, 0.4, and 0.1, right? And what we would do then, if we follow along with this definition of this formula that we established, right, we would just sum up each outcome times its probability. So 0 times 0.2 plus 1 times 0.3 plus 2 times 0.4 plus 3 times, right? And we would get this 0.3 plus 0.8, 1.1 plus 0.3 is 1.4. So what we're saying is that if these are our possible outcomes, on average, if we were to do this event, this random variable x, a large number of times, our average outcome would be a 1.4. And that brings us to an important point when it comes to expected value that you should know, is that expected value is the same thing as the mean. This process might look very familiar to taking a weighted average, right? Like the way you might calculate your grade in a class, where you have like exams, homework, quizzes, and each of those has a particular weight. And you go through and you multiply your average in each category by the weight to get your overall grade average. This is the same idea, right? We're taking each outcome and weighting it by its probability. So expected value is a weighted average. It's a mean of the probability distribution of x, right? And as we have a larger and larger sample, right? So like maybe our sample's quite small and our distribution looks something like this, right? Bell curve, mean is roughly in the middle. As we take more and more, a larger and larger sample, right, our distribution will get more and more narrow around this mean. We'll be able to predict what will happen with more accuracy. All right, so let's try a practice problem. A state fair is having a raffle in which tickets cost $1. All 2,000 tickets are sold. 32 tickets will be selected to win prizes. So of those 32, 20 people will each win $25, 10 people will each win $50, and 2 people will each win $100. What is the expected value of one ticket? So let's go through and use our formula. Expected value of, we'll just call this x, right? X, random variable of our winnings in this raffle, right? And we go through, list the outcome, multiply by its probability. The first outcome, we could win $25, right? And what's the probability of that happening? Well, there's 20 people who will win $25 out of, is that going to be 32 or is that 2,000, right? It's 20 people out of the total of 2,000, right? Next possible outcome, $50. Right? We'll multiply that by 10 people out of those 2,000 will win $50 and so forth. 100 times 2 out of 2,000, right? And you might think, okay, now we're done, right? We listed out all of our possible outcomes and the probabilities of each, but we're missing out on our one validation step that we need to do, which is that the probabilities of all the outcomes need to add up to 1, right? We need to account for all the possible outcomes, right? If these probabilities don't add up to 1, we haven't accounted for all the possible outcomes. Right, clearly these don't add up to 1, right? 20 plus 10 plus 2, that's 32, not even close to 2,000. So what's the rest of the probability, right? It's all those people who bought a ticket who didn't win anything. So we have to account for them because all of those people will have lost $1, right? So the additional outcome we need to account for is minus 1 times the probability of losing $1, right? That's everyone who didn't win a prize. So 2,000 minus 32, 1,968 out of 2,000. Right, vast majority of people are not going to win anything. In fact, they're going to lose $1 because that's what they used to purchase the ticket, right? And if we put this all into our calculator, we will get negative, let me double check what I had, negative 38 cents, right? So let's interpret what this means. This doesn't mean that any one person is going to lose 38 cents, right? That's actually impossible in this situation. Either you lose $1 or you make, 25, 50, or 100. But what this means is that with sufficient tickets, right, on average, the average person is going to lose 38 cents. So if we take all the people who bought a ticket and average out their winnings, it'll be losing 38 cents, right? That's an important idea to keep in mind, right? That's the average of this distribution, this probability distribution for the random variable X is losing 38 cents. So that brings us to our next question. A casino game costs $1 to play with prizes of $10, $20, and $50. However, the expected value of one play is minus 95 cents. Which is the best way to interpret the expected value in this situation? Let's look at our answer choices. There's a 95% chance that a given player will lose money on a given play. B, on average, players will lose 5 cents when playing this game. C, on average, players will lose 95 cents when playing this game. D, the next player to play this game will lose 95 cents. So we want to ask ourselves, which ones can we rule out entirely from the get-go? All right, we know expected value is a mean, right? It doesn't have to do with chance or that doesn't translate to there being a 95% chance of anything, right? So we can rule out A, right? And then I think a lot of people will be tempted to look at D here. But as we said on the last problem, right? Expected value doesn't have anything to do with one individual person, right? One individual person is actually impossible to only lose 95 cents in this game, right? But if we take all of the people who play this, right, a very large number of people, and we average out their winnings, that will come out to losing 95 cents. So on average, players will lose 95 cents when playing this game. And then, doing these expected value problems can help you determine whether a game is in your interest to play, right? Obviously, if on average people are losing money, you can expect, the more and more you play this game, odds are you're going to lose money. But hopefully that all gives you a better idea of expected value. Key ideas to remember, same thing as the mean, just add up all of the outcomes times their probabilities. And yeah, hope that helps.